Hello, welcome back to class. This is Mr. Brain, and we are here to discuss sound wave. Okay, now sound wave is one of the courses in your WIEC curriculum or syllabus for physics. Okay, so what to quickly look at sound wave, and now in sound wave is a wave that is transmitted through a material medium, like you all know. All right, sound wave, the mechanism of sound wave is that it's vibrating air column so that the air column has a compression and a release, which we call rarefaction, okay? So one side of the air column is compressing and the other side is rarefacting. That is what we call sound wave, okay? So sound wave requires material medium to be transmitted, okay? And every wave that requires material medium, they are all what? Mechanical wave. So sound wave is one of those mechanical waves. The next one is that sound wave is a longitudinal wave. So what is longitudinal wave? Longitudinal wave is a wave that the vibration and the wave motion are in the same direction. Okay, so the vibration is this way, the wave is traveling the same way. So that is a longitudinal wave. And sound wave, in this, for instance now, sound can travel through air, and not just air, it travels through metal, concrete, solid stuff. And the speed of sound wave in all this material are faster than air. Okay, I'm sure some of you are not aware. The speed of sound in air is about, let's say, 330 meters per second. But the speed of sound in water is about, let's say, 1,500 meters per second. Alright? The speed of sound is string. Alright? Your string instrument, like the guitar, is about 2,000. Okay? 2,000 meters per second. You can see. The speed of sound is faster, or sound travels faster in what? Concrete or string than in air. Alright? Okay? So now, instead of pressure, when you talk about pressure, when we are discussing pressure, we're talking about gas, okay, that's air, alright? The pressure of air does not affect sound speed or sound wave, okay? So pressure has no effect on sound wave. Echo. What do you call echo? When we discuss the properties of wave, we talked about reflection, right? So we say sound wave. And we said all reflection of wave is what? The ability, alright, for wave to strike a medium and change direction. Alright? Wave coming across or intersecting with a medium, a plane surface or medium, and changing direction. Sound wave does reflection very well. In fact, that is where echo comes in. Okay, so what is echo? Echo simply means when a sound wave travels and hits an obstacle, then comes back. Alright, so if you are mostly in an empty environment, when you have concrete wall, you make a sound, the sound travels, hit an intersection or a block, and getting it, making the concrete itself, and comes back. Alright, that forms an echo. So sometimes you repeat it often. Now, echo is very important because echo is used to determine the speed of sound, okay? And also is used to determine the depth of the sea, alright? That is what sailors use to determine the depth of the sea, alright? So an echo is also used to determine, the nature of the mineral, alright? During mining, they use it to detect minerals that are, alright, on the surface below, okay? So now, what can we get from echo? Remember, we said when sound travels and is intersected by a wall, okay, it turns back, alright? So now it covers this distance and another distance, okay? So when we want to calculate the velocity, which is velocity of sound, that returns is what? Velocity is linearly distance over time, okay? So this time around is what? 2d over time. 2d over time. I hope you understand. Alright, so this formula is very important in calculating many things and it has many applications, okay? So we move on to this. Now, what is this? sound has frequency, and we talked about frequency, okay? Frequency is about the number of oscillation, alright, that can be made in 1 second, okay? Alright, so when you talk about the frequencies of sound, and then when you have sound of varying frequency, a little bit different, alright? The difference between those frequencies is what we call pitch, okay? When sounds of frequencies that are almost, closely related are sound together, the difference between those frequencies, alright, is what we call pitch, okay? Varying frequency, that is what we call pitch, okay? So what is pitch? Now pitch is talking about, high frequency or low frequency, or you say note. I think the next one is note, okay? Note, alright? So when we have a sound of low note, alright, or tone, low note or tone, we say it is what? It has a low pitch. Then when someone shrill, we say it has a very high pitch. Okay? So high pitch is symbolic to what? Shrill. Are you with me? Right? You make a very, high note. Alright? Those in the musical field understand when we talk of note, high note and low note. Okay? So now, we have what we call ultrasonic waves, okay? Now, when a wave becomes ultrasonic, it means your ear can no longer detect the frequency, okay? So, human beings, we can detect a frequency of 20 hertz, alright? 20 hertz to 20,000 hertz, okay? So, any frequency above 20,000 is ultrasonic. Remember, the human ear can detect a frequency within the range of what? 20 hertz to what? 20,000. So all the frequencies above 20,000 are ultrasonic sound, okay? And you have, this animal like dog. Dog can detect those frequencies. Alright? So now, they use those frequencies to communicate with themselves, from a very far distance, that is the belief anyway. So now we have intensity. Intensity talks about loudness, okay? You can see intensity or loudness. And this is about the power, alright, the power of sound transmitted within an area. Alright, it's a measure of the power of sound transmitted within an area per unit time. You understand? That is what frequency is all about. Now, frequency is directly or is dependent on the amplitude of the sound. Alright, the amplitude. So take note. This intensity or loudness is dependent on what? Amplitude of sound. Please take note of this word. Amplitude of sound. Meanwhile, your pitch, alright, and your pitch, alright, they all depend on what? The frequency of sound, okay? They all depend on frequency of sound. Intensity depends on amplitude, then your pitch depends on frequency and also pitch, alright? These are the few things we want to look at. Then also, now, vibrating strings, okay? In sound wave, we look at sound wave, sound wave has to do with vibrating colors, okay? When air molecules are vibrating. So, in sound wave, we look at, the string instrument and the wind instrument, okay? So, the string or vibrating string, we want to start with that one first. So, they include the guitar, violin, and piano. These are instruments, alright, whose source of sound are from what? Vibrating strings, okay? So, we want to look at how, you can make. We want to look at how this thing works. Okay, how does this thing work? Now, watch. When we make a sound, alright, there are different notes that we make from a string. Are you getting it? When you make it, when you are playing a guitar, there are different notes. Or let me say different sounds that you can hear. Alright? So all those sounds have their notes and they all have their frequencies, okay? So now, but there is one that we call fundamental frequency, okay? And this is that fundamental frequency. That's the very first note that you can make from a string instrument. So all string instruments, as soon as you plug a string instrument, alright, it either goes this way and comes back this way, okay? So that is the first note that will be made, alright? And if you look at this, alright, When it goes this way or that way, that is, alright, half wavelength, right? You know, half wavelength. What is the full wavelength? The full wavelength is when you go up and down, right? So if you now this is not going up and down, it's like going this way or that way. Both of them consider. Now, when it goes up and under, this is one wavelength. So when we have half wavelength, this is half wavelength. So this is a half wavelength, alright? So this length from here, alright, to this place is half wavelength. That is wavelength over 2. Alright? So we say half wavelength is equal to what? The length. And when you cross multiply, one wavelength is equal to what? 2L. Can you see that? Alright? Now, meanwhile, there's a formula to determine this, okay? Now, I need to discuss that formula. For you to understand that formula, you must know that when it comes to string instruments, the frequency of sound is directly proportional to the tension, alright? Sorry, directly proportional to the square root of the tension and inversely proportional to the what? Mass per unit length, okay? The mass per unit length directly proportional to the square root of the tension and inversely proportional to the mass per unit length, okay? Now this is the constant. Now this is the constant here, 2L. Are you see that? That's the constant, okay? Now, and this is what we're seeing here, alright? This constant is what we are trying to determine in this place now. Are you getting it now? So, now this is how we calculate the frequency for, and remember, this is fundamental frequency. Why is it fundamental frequency? Remember that the length is, the lambda is 2L. Are you see that? 2L. You know how we got this, right? Okay? So, fundamental frequency is related with F naught. Please take note. Fundamental frequency is related with F naught. You can only explain that in English to understand some of the things we have said so far. Fundamental frequency is represented with F naught. And I said before, when you are making frequencies with, a guitar, there are different frequencies you can make, alright? So, it's not just the fundamental frequency. After this, there is the next note that will be made, or the next tone. Okay, when I say tone or note, I'm talking of frequencies, okay? So the next note that will be made, this is the fundamental. The next note that will be made, let me change this part of the board, alright? The next note that will be made, alright, under the string instrument is when we have, when the string goes up and down, remember, right? So either it goes up like this and comes down, or it goes this way, alright? So once the string vibrates in this manner, that is the next note. Remember, this is the first note, alright? And this is the next note that will be made. This is the vibration that will produce the next note I made, alright? So now, if this is the first note, the next note, and the next one, they are called overtones, okay? So we have what we call overtones. Or we call them harmonics, okay? Harmonics, okay? So what is an overtone? An overtone is the frequency that will be made after the F naught, okay? So remember, if the F naught, the lambda is half, right? For F naught, the lambda is half, right? So for the next one, alright, the first overtone, which is F1, the lambda is what? This is half, this is another half. So that's 2 half, right? So we say that the first overtone is what? 2 F naught. Alright? So what does this mean? It means that if my F naught is 30 hertz, okay, my next overtone, alright, sorry, my next overtone, which is 2 F naught, will be what? 60 hertz. So my first overtone will be what? 60 hertz. You understand the meaning of this now? I'm just explaining, okay? So now the second overtone will be what? Now the second overtone, let's do a diagram for that. So the second overtone, we have that what? It goes up, comes down, goes up again. Alright? So it goes up, comes down, goes up again. So what can you see from this place now? Alright? Literally you can see that what? You can see how many lambda? 3 lambda, right? Sorry, half lambda. How many lambda? Remember, the test fundamental frequency is what? What can you see? half lambda, right? So 1, 2, 3, that is what? So, or you can do it this way, alright? Let me do another way. Another way to, analyze this is that you can see how many lambda is here. This is what? 1.5. 1.5 is equal to 3 over 2, right? 3 over 2 lambda is equivalent to the length, right? So when you cross multiply, what does that show you? That means that the lambda is what? 2L, right? Yes, 2L over 3, alright? 2L over 3 when you cross multiply. Can you see that? Alright? So now, what does that show you? Alright? What does that show you? That shows you that what? That shows you that what? It means that, remember, if we want to talk about if you want to talk about one frequency size F naught is what? F naught is equivalent to what? Half lambda, right? Half lambda. Now, how many half lambda is going to give us this? That would be like 3, right? 3 half lambda. Look at it. 3 half lambda will give us 3 half lambda, alright? 3 half lambda will give us this 2 over 3. I don't know if you understand it. So, therefore, we say that this is what? 3 naught, okay? So, the second overtone is 3 naught. And that is how the harmonics go, okay? So, what are the harmonics? The harmonics is naught, 2 naught, right? 3 naught, 5 naught. So, it follows a whole number alright? You know what I'm saying, right? So, this is for what? String instrument. Now, it goes a little bit different when we go to pipe instrument or wind instrument, okay? So, I think we understand this. Alright, so these are, the things that will help us to do calculation. We are coming to that very soon, and we're going to do calculations of this. Remember that frequency is directly proportional to what? The square root of tension, okay? Alright, and another thing you need to know, when it comes to temperature, alright, temperature affects sound. Temperature affects sound. The sound is louder or the sound travels farther when the temperature is lower. Alright? Once temperature is lower, it travels farther. You understand it? So what does it mean? It means the higher the temperature, the lower the speed of sound. And the lower the temperature, the higher the speed of the sound. I hope you understand that. Alright, so we're going to do up a video going to discuss pipe instrument. I'm going to look at the formulas under pipe instrument. I hope you understand this. Thank you.